So this is my investigative phenomenon
And by me, Citali, Toscano.
project by Karina Hernandez, which is myself. I have a couple of research questions. So like, why do some liquids float on top of others, and why don't some liquids mix? What is stopping two liquids from mixing in with each other? All this has to do with density. Density plays a major part on as to why certain liquids lay on top of each other. So density is the degree of compactness of a substance. In other words, it's the measure of how tightly the stuff is packed together, or how much a substance takes up. It is the amount of mass per unit of volume, and it's P equals M over V. P equals density, the measure of how tightly the stuff is packed together. M equals mass, the measure of how much stuff there is in an object. V equals volume, which is the portion or how much there is. So they're all kind of related. So if if a liquid or an object is less dense, it is going to be like the picture on the left side. And if it's more dense, then it's more compact and it's everything more together, and it should be heavier as well. So an object can be denser than the object next to it, and they couldn't look exactly the same, because just because they look exactly the same doesn't mean that they're going to weigh the same. One of them could be denser. So if something is more dense, then it is going to weigh more. If it is less dense, then it is going to weigh less. Sometimes two objects, they could look the same, but doesn't mean they have to weigh the same. So water versus isopropyl alcohol. Well, with liquids such as alcohol and water, these two look exactly the same. Water is denser and therefore weighs more. The density of water is 1 gram per ml, and the density of alcohol is 0.785 grams per ml. And then the G is for grams, ml is for milliliters. I poured about half a cup of water on the left cup, and then I poured about half a cup of isopropyl alcohol in the right cup, and a half cup of liquid is about 118 milliliters. And as you can see, the water weighed a little bit more because it is a little bit more denser than alcohol. If I were to pour 50 ml of isopropyl alcohol in water, the water would remain at the bottom and the alcohol would remain on top of it. They might mix a little bit because water molecules are polar and the alcohol molecules have a non-polar and polar parts. This means that there are hydrogen bonds being able to form with the water. However, water and oil do not mix at all. So water versus vegetable oil. The water molecules attract each other and the oil molecules stick together. That's why the oil stays on top, they stick together, and then the water molecules, they want to stick to each other, so it remains at the bottom, they don't mix. This reaction to the molecules causes the oil and water to form two different layers. The water molecules pack closer together, therefore they sink to the bottom of the glass. The density of the vegetable oil is 0.92 grams per ml. The molecules of oil are a bit bigger than that of water. Opposites attract, and therefore the water molecules stick to each other instead of the oil. Water is polar, and the oils, any type of oil, vegetable oil, olive oil, they do not have any polar parts. So even if I try to mix them with the spoon, which I do later on, the two liquids, they remain separate. They form bubbles, but they do not fully mix.
When liquids do not mix, they are said to be immiscible. The word miscibility describes how well two substances mix. Oil and water do not mix, therefore they are immiscible. And one of the reasons why they don't mix so well is because liquids that are more dense are also heavier and are at the bottom, and the liquids that are the least dense will stay at the top. So the thing is that water usually has less hydrogen atoms within it, and the oil has more air within it. So that is why one of the reasons why they will not mix. And Furthermore, water and oil will not mix due to something called intermolecular polarity or intermolecular forces. So basically this means that each molecule has its own polarity, which is the separation of charge, causing it to not want to interact with others. So in this project, the water, the oil, the dish soap, the isopropyl alcohol, and the corn syrup will be layered on top of one another. And the independent variables were found to be the water, oil, dish soap, isopropyl alcohol, and the corn syrup. As for the confounding variable, we did find one, which is density, and the confounding variables are the spoon used to help layer the liquids into the cup, as well as the rate and speed at which each liquid is layered. As mentioned within this experiment, if you pour the liquids into the cup too quickly, it will cause some of them to mix, and it will actually cause it to not be able to layer as nicely as you would like. And this would actually affect the results of the experiment. Before you actually start the experiment, it's important that you take the density of each thing that you will be using. So the corn syrup is 1.4 grams over milliliters, the dish soap was 1.03 grams over milliliter, and the water was 1 gram over milliliter. The vegetable oil was 0.82 grams over milliliter, and the isopropyl alcohol was 0.7854 grams over milliliter.
So in this slide, you see the layers, which at the very top you could see it's clear, which is the isopropyl alcohol, and then at the bottom of that, it's the vegetable oil, which is the yellow layer, the yellow liquid, and then you see the water, which is pinkish because it did mix a little bit with the dish soap, and the dish soap is the redder one. And then the corn syrup is all the way at the bottom. And you could see more right here. This picture is with flash. I layered the liquids from heaviest to the lightest. So in other words, the denser liquid is at the bottom and the least dense liquid is at the very top. So I noticed that after mixing the liquids, the syrup would like grab onto the spoon because it was so dense. I would try to get it, but then it would sink back down. And you could see how the spoon and the corn syrup is like grabbing on to the spoon, but then it goes right back down. It doesn't even go past the dish soap. I also noticed that the dish soap and water, they did mix. The vegetable oil and the dish soap made bubbles. The alcohol also mixed with the vegetable oil, but it quickly layered into a different layer again. So you could see the bubbles and the yellowness, but then after some time, you could see the rubbing alcohol or isopropyl alcohol at the very top. And the corn syrup and the dish soap, throughout the whole experiment, you could see how they do not mix at all. So this is when it's settled, and you could see how the dish soap and the water, it did mix, and then you could see the bubbles with the oil on the soap, and then you could see the layer of the rubbing alcohol on top, and at the very bottom, of course, you could see the corn syrup, which is very, very dense.
So the lighter liquids, such as the isopropyl alcohol and water, are less dense. This can be because alcohol is made of carbon and hydrogen, so it's pretty light like oil, but it also has oxygen, but not as much. You might think it would be a little more dense than oil, but the alcohol molecules do not pack very closely. And when it comes to the water, water is the most dense as it is made of hydrogen atoms and oxygen atoms. This means that they have less stuff packed into them. And so from this experiment, students can realize that the top layers are less dense than the bottom layers. Students can quickly learn to let each layer settle before adding the next one. It is important to take the time to pour slowly and let the liquids settle. This is because if you put the liquids into one another too quickly, it can cause them to mix and it can actually create it much harder for the liquids to begin layering, and it'll take a longer time. Also, when pouring the lighter liquids, it is easier to pour from the side of the cup instead of directly pouring it onto the liquid under it. Another great example is that you can use a spoon. just put the spoon very, very closely to the nearest layer, and then just put the other liquid that you're going to be putting, so that, like I said, they don't mix as quickly or as easily. So now we have the NGSS, and this is the way to tie up the experiment to the NGSS. In the area of science and engineering practices from the NGSS, one of the standards is to analyze and interpret data. This experiment is a great example for students in the grades 6 through 8 to be able to physically see that liquids are able to layer separately. To further make sense of the way liquids layer, they can research the densities of each liquid and predict why some of them float on top of each other. For example, this experiment would allow them to develop a model and observe the changes, as well as predict how some molecules react to other molecules. In the CCC of the NGSS, one of the standards is systems and system models. It is important to realize the different measurements of densities and their proportion to other liquids, as they are all different. For example, the density of water is not the same as the density of dish soap. We define the boundaries of each liquid and make a model out of it. In the DCI of the NGSS, one of the standards is 5-PS1-3, Matters and its Interactions. Students can make observations and measurements to identify materials based on their properties. For example, the water's density will never change, and the student will know that 1 gram over milliliter will always be water. Here is an example of the NGSS for 6th grade, which is at the middle school level, and it is the structure and properties of matter. So in this area, students who demonstrate understanding can develop models to describe the atomic composition of simple molecules and extended structures. They will also be able to gather and make sense of information to gather that synthetic materials come from natural resources and impact society. And the last expectation or understanding would be to develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. And then below them are the science engineering practices, the disciplinary core ideas, cross-cutting concepts, and you can look further into that information on their website. So I think that it's important to always explain to students why they are learning what they are learning, especially because, many times they're taught, about buoyancy and density, but they don't really know how to correlate that back to life. So this experiment, you can teach them that density is important when it comes to our environment, especially with ships and submarines and oil spills. And you can always, explain to them how density has an impact in our environment. With ships and submarines, you can tell them that, the object's density is less than the density of water, then it will float. If its density is less than enough water, it will sink. So ships can float because, they're able to hold more air, which is able to propel them to float at the top of the water. And then when it comes with oil spills, this is a great way to showcase how this experiment is an example of oil spill, especially because, like ships, oil floats because it is less dense than water, but unlike ships, oil requires no special engineering. So oil is naturally less dense than water, which is why even if you mix oil and vinegar, the oil will not mix with the vinegar. It will stay at the top. And so, like I said, this is a pretty good way to teach about density and correlate it back to life, so that they're able to tie it back to something and get a better understanding of it. Here are the references that were used to help develop this experiment. First is the Amazing 9-layer density tower, the next generation science standards, and how to stack liquids in a rainbow of layers. This is the last reference is a great example if you ever need to look back and basically see another example of how to do this experiment.